Hello students, in this video we'll consider the Dirichlet problem on an annulus. Let's consider our Dirichlet problem on an annulus. Okay, and so what will this look like? It's going to be the following problem. It's going to be Laplacian of u is equal to 0 for r1 less than mod z less than r2, like that. And then it's going to be piecewise defined. U of r1 e to the I theta is going to be equal to a temperature T1 constant, and u of r2 e to the I theta is going to be a temperature T2. Where here T1 and T2 are constants, so these are constants over here. Okay, so here's our setup, right? Our setup is there's a little circle over here that we punch out. The radius of that is going to be r1. Then I have a bigger circle over here. The radius of that's going to be r2. U is equal to T2 over here. U is equal to T1 over here. And the key feature about this region, of course we want Laplacian of u to be equal to 0. We want to find a harmonic function inside the annular region. Okay, that's our setup. Great. And so now what we're going to do is the following. We're going to recall Laplacian u is, in polar coordinates, is urr plus 1 over r ur plus 1 over r squared u theta theta, right? And so if we ask the question, what are the radial harmonic functions? What are radial harmonic functions? What are the radial harmonic functions? That means we're just looking for a function for u of r and theta that have the form just f of r, right? So if we plug that into the problem, what do we get? If we plug that into the problem, we're going to have frr plus 1 over r fr is equal to 0. Great. Now hit that with r. Of course, implicitly when we're doing this, we're assuming that r is not equal to 0, right? So we're doing the Laplacian, we're avoiding the origin, okay? Which the annulus happens to do, right? The annulus I'm avoiding the origin by doing this, right? So this is r frr plus fr is equal to 0. What we can do now is we can say that this is really d by dr of r fr is equal to 0. So that says that r fr is a constant. So r fr is a constant c1, which forces fr to be a constant c1 over r, right? And therefore, this says that f of r is going to be c1 log r plus c2. So this is harmonic in any region that doesn't contain the origin. Harmonic in a region without 0. Okay. So good, so I know logarithms are harmonic functions. In particular, this will help me construct a harmonic function in this to solve this problem, right? So what are we going to do now? Let's consider the function u of z, which is t1 plus t2 minus t1. Then I'm going to have the ratio of logarithms, the log of mod z over r1 over log of r2 over r1, okay? This function u is a harmonic function. So u is a harmonic function. That's good. Let's make sure it satisfies the right boundary conditions, right? What is u of r1 e to the I theta? Well, it's going to be t1 plus t2 minus t1, the log of r1 over r1 over log r2 over r1. But the log of r1 over r1 is just the log of 1, which is 0. So this is just t1 plus t2 minus t1. And that times 0, right? And that's just t1. Good. So it satisfies the right boundary condition. So u of r1 of e to the I theta is t1. So I have harmonic functions right over there. What about the other condition? The other condition was u of R2 e to the I theta. Okay? Well, what will this be? This is just going to be what? This is just going to be T1 plus T2 minus T1 times what? Times the log of R2 over R1 over the log of R2 minus R1, right? Those are equal to 1, and so this is just T1 plus T2 minus T1, which is just T2, right? So this is equal to T2, and we have our boundary condition satisfied. So I found the right harmonic function that does this. Now, this harmonic function, just as a note, this harmonic function comes up a lot because what I can do now is I can solve this problem in with the center of the circle being offset, right? So if I have an offset center like this, as long as I punch out the origin, right? So just a remark, so if we offset the center, is offset, composes with a Blaschke factor. Okay, what will those Blaschke conformal automorphisms do? Those Blaschke conformal automorphisms will move that offset center into what? Into one where the origin is at the center, right? We've seen this in a previous video, which we can link to. The Blaschke factor is going to give us what? Now that gives us something really neat too. If I plug a Blaschke factor into the logarithm, what I end up getting is I get something that comes up a lot in hyperbolic geometry, right? It's a hyperbolic geometry thing, right? It helps me see what the hyperbolic metrics going on over here. So offsetting these things, so it looks like the solution to these steady heat problems in an annulus, or in a sort of a region with between two circles where the origin is encapsulated, is related very closely with hyperbolic geometry, and we'll explore that in further videos. Thank you very much.